Okay. Do you hear me?
Yes.
Okay, I begin with the conference. The lecture will be Danilo Oril and me. Then I begin with my part about this invitation about to the state of the art of artificial intelligence and optimization in this moment. Okay, I begin here. Okay, you are looking the screen.
Yes.
Okay. Good morning, for all. We appreciate that you assist to this short conversation about the here and now of artificial intelligence and the state of the art of optimization. This is the central part of of this conversation, the first part, and we have two part additional that are application in this moment in the area of modeling in the sector port. Okay, here I begin with this first. Okay, this is valid. This presentation is valid for any type of system. Okay, it's not only valid for the port sector or for any sector. This is the state of the art of optimization, and is the what is intelligence, artificial intelligence in this moment. Okay, uh, first we are in artificial intelligence. Artificial intelligence is the most in this moment is are changing all things in the world. 10 years ago, the situation was very different, but only 3 years ago, with the situation that we begin to live with GPT solutions, and that was a new approach for artificial intelligence. All the people, the majority of the people or the professional know that this type of situation that the artificial intelligence has changed in the traditional part of artificial intelligence. Okay, all the majority of the companies, of the big companies, are beginning to try to develop his own applications using GPT. Basically, um, this is the first. Then, and the change in the area of GPT is very the speed is very high in this moment, and in 1 year all change, in 2 years all change, and in this moment we don't know what is the end of the we call GPT. Okay, this is the fifth part of artificial intelligence. Why we make a difference? Because we have two types of artificial intelligence. The first is the the intelligence related with the traditional artificial intelligence that is like GPT. Okay, they try to learn about the reading to study, to process with very, very big um, models, LL models, developed learning with models with enough parameters to change all. I say 5 years ago, we was making or more. We was when at the end of the traditional neural nets epoch. Okay, we have many types of neural nets. Okay, but with the arrival of GPT, we only have one neural net. And this type of neural net is fully uh, related uh, with learn automatically. Okay, this is the first characteristic. We don't have think in this moment to learn using using another model different than GPT and to use very high power computers. Okay, what happened with the state of the art of optimization? Why we divide the title of the conversation? Because the people, the professional, don't use, see, in the traditional, we don't use this part of artificial intelligence, that is the prescriptive artificial intelligence. Okay, then the majority of the professionals don't don't make modeling, mathematical modeling. The name more specific is mathematical programming models. Okay, and we don't have peoples that know this type of artificial intelligence that don't do it, that don't have a very strong in his capabilities. But the reality is that in this moment, the view of the optimization is very rapidly, is similar to the GPT solutions, and we have solutions similar that the solution based in the power of computer, say power computing, okay, that use these very strong computers to solve very high models. This is the situation in this moment. What will happen? We don't know. We only know that the winner at the end is who see that the create the knowledge. See, this is the question. Who at the end, with this speed of growing, can will be will be the winner. And it's possible that the winner will be a machine because in this moment, the power of the machines is very, very high. The start of the optimization is based then in this accumulation of algorithms, artificial brains, and power computer. Okay, obviously, and the investment return, because if you don't have enough investment return, you can grow in this type of applications. Okay, then there are many things that are happening that are officially happen during in this moment. First, we can make models in a different way. Okay, we can assemble models like a Lego model. It's very different. The people don't think what happened with the models that we make programming. Now we assembly the parts of the models. Okay, then this is Optex is our is of our tool to make models, and it's based in an expert system. An expert system is the way to don't use programmers. Okay, this is a reality. We begin to make models without programmers 30 years ago. Okay, this was the beginning. So yes, 30 years ago. Okay, then what happened? We begin to develop the ideas of the expert systems. That is a area of the artificial intelligence that was used in this moment 30 years ago in the to make expert system of humans to help the people, the humans, to take decisions based on the experience of the person. But when we develop systems based on mathematicals, the expert systems are perfect because the mathematical are perfect. Then the big difference between a normal expert system and an optimization expert system is that the optimization expert system is perfect. See, don't have errors, then don't make inference what happened. The optimization expert system is perfect because he understands the mathematical, then he can develop all. Then, for example, this is the reality in this moment. We can, in mathematical programming, we can use this type of to put together the models in mathematical programming. Okay, I have two models. I can make the models like Lego, and we can join the models, and we have another mathematical model, model, only jointly, seeing and making or dividing. We have the two the two the two models. This is one advantage because we can divide the models in the amount of model that we need. Okay, this is different to begin to make models using this. Okay, and this is the dream or the all mathematical model. Don't use equations, only use say, please put this together. And this is the situation. Okay, then the best situation in this moment for 30 years ago is to to don't make programs and make expert systems and put it together. This is the reality 30 years ago. Okay, this is, and he has evolved are grow with the type of computer, because first we can use to put together edge computing and cloud computing. And in this moment, we can point together any type of network, okay, any type of network in this moment. Okay, and these are grew, for example, NVIDIA. NVIDIA, we know about the NVIDIA, all the power that that offers in for traditional artificial intelligence, for forecasted artificial intelligence for GPT models or LLM models. Okay, this is we know that this was the first one of the first steps, and all the people know that there was NVIDIA, one of the large companies in the world in the that grew very rapidly. Okay, then we make many architectures in this type, because we can make a specialized edge computing and cloud computing. Okay, and this is the type of super computers of 3 years ago, in which we have a cluster in the cloud computing. We have a cluster of CPUs, and we have in the edge computing part we have GPUs. GPUs solving problem. The easy GPUs in a similar way that in the GPT, in the GPUs are specialized in this moment, are oriented to solve problems using specialized GPUs. Okay, for me, 5 years ago, I don't you heard about the NVIDIA making optimization. Today they have labs and laboratories that in which they are making new models, the specialized software and hardware to have a very special GPUs. Okay, and they are making examples. They in this moment they can are develop all the algorithms, are all the part of how we can use the optimization in NVIDIA. The situation is that it is different. The difference in the type of the how are the algorithms for a normal CPU, which is the different with a CPU oriented to a GPU. Not different. Different. They are solved, and they are making a solution, and in the moment in the market you get solution. Then the state of the art is that we can use an expert system of artificial intelligence is the start point in this moment. We link this with the text that understand the optimization expert system, and in this moment of text produce standard the code that we call produce the cognitive robots to make the situation. And this possibility give us the situation to make a multi-problem mathematical model, multi-problem mathematical models. Then we can develop the idea of artificial hypothalamus of different company for different objects of different systems. Okay, this is an oil and gas hypothalamus, which was the idea in high that we are studying in the neuroscience. We are not working based on neural nets. We are working based on the human brain to build artificial brains. And the hypothalamus is the central part of an artificial brain. Okay, and we can have now, we have the big difference with the standard vision of the to make a run in this moment is to have that all models that we need in any space, all models can run simultaneously and automatically. Okay, because they don't need before in the industry 4.0, we begin to change how will be the new technology, and is necessary that this change. And this is the situation, okay, that we need hypothalamus for any point of view, from the point of view a company, for the point of view of the parts of the company, for the point of view of the administrative uses of the system. Then we have in all part this type of tools to work. This is reality in this moment, and we begin to work many years ago in this direction. We make near to the first part that we developed was multi-model, multi-problem models. Was the first we developed this by 30 years ago. Okay. Now we are in the new version, in the new epoch. That is of text. That is the quantum computers joined with artificial intelligence. This normally this is quantum AI, artificial intelligence, and this is an idea of the Feynman Nobel Prize in many time ago. Okay, more than 30 years, he began to think in quantum computers, and today we have quantum computers. This is the new reality. Then our expert, our mm, objects of our this new situation is that we have evolved from the joint the first system with the super server, okay, basically in GPUs, and we changed to develop now the same idea but using um, computers, quantum computers. This is the same, is equal relatively, but is then we migrate the basic ideas about the state of the art of the optimization in to make automatically models. Okay, we migrate from the super servers to the quantum computers. Okay, it's very easy to work in this. It's very hard. The people working, there are eight, more or less, companies that are working in this area to make to develop quantum computers. Commercially, is ready because in this moment there are a special company that has his own power, his own computer quantum computers, okay, and they are making um, investigations, research about this. The result in the moment of the investigation is that there are a new there are a problem, not a problem. There are a difference that we need to learn about. That is the super server algorithm and the quantum algorithm are different, are not equal because the qubits and bits are different. Then we need only to change this part of the system, okay, that are the new algorithms. The algorithms are complicated and is necessary to learn about. There are a big problem in this moment that is that the companies that they develop many models use programmers. Then they have problems to make the migration because they reprogram, recode all the situation. This is the new situation, okay, in which then we produce this program in the algorithms of this. The another part that is very important is the mathematical model stores. What happened? As all in the world, okay, we have stores in this moment of all. Okay, this is the production of software. This is the production of software using software factories. Okay, then it's important that it's very difficult for many people to learn in this moment to begin to learn to drive a new technologies because they don't know about the new technology. They don't have practice. So there are many um, there are a little of people that have that are working for many years in this area. Then the people that can make the models are very few. Okay, but in this moment, with a factor, we can make factories using tools like Optex that we don't need to write programs. Okay, we can develop models in 1, 2 weeks. Complex models, real models, is the situation. No academic models, models for the reality. It's important that with the power of computer, new power of computing, the models are every day is similar that the GPT. The models of GPT they are bigger. Okay, the modeling optimization is they are bigger because we have the same power. Okay, the same power, then it's possible the model that has 3 equations when I was studying, okay, today has millions of equations and room is equal. The big difference is that the prescriptive artificial intelligence include equations, include models, include another types of power that the people don't use and don't know. Then they need to begin to learn. And one way is to make we use a factory that produce this automatically. Okay, this is our model. Then where are the artificial intelligence tools for optimization for this? Okay, the first is that we have an optimization expert system. Then an optimization expert system is very easy. It's a database, a very structured database, but it's possible to develop a tool like based on GPT that learn about this optimization expert system. Then it's possible to make the models fill the expert systems using GPT. Then in the future, in the near future, the people, see, the people make models in a similar way that GPT, not because are the same methodologies, is because GPT can help to substitute the people. In the moment, as it will be that the people that never learn about to make models learn about to make models directly without understand only with a prompting engineering he can say, and it's possible that the GPT understand and feel the expert system. This is the part, the central part of this. The another two parts. The first one is related. Okay, one part is related with, excuse me, here is related. I don't speak about this, but this is the situation. This was a webinar that we um, keep the 1 year ago, okay, for German Association of Engineering. The lecture was Danilo Abril and me, and we tried two topics. One, the problem of has toward cleaner ports. We need to have in the future um, more cleaner ports, cleaner in all directions, less energy consumption, less contaminant emissions, production, less all the happening in the moment near to the problem, to the multimodal systems. This is more important. The future, which is the future of the ports, the future of the ports are multimodal, mega system, port and railway mega system is the center part. Okay, like for example the port of Callao, in which we are thinking in to have only one port, see, in Chancay, and you and put together El Callao and Chancay and use rail to link the two ways. But this is standard in the moment. For example, in Miami, the project Net Zero are working in this direction. Okay, they are making um, ports out. They are changing the vision of the port of Miami because they have a dry port near to Fort Lauderdale. They travel through rails to the two ways to Fort Lauderdale, and then in this hub they accumulate all the cargo and continue in the two directions the link with another hubs in which we put the cargo that arrive by the drive of the port of Miami. This is the way in this moment in this. The another part that I give the I that Danilo Abril was speak and present is the evolution of the ports in this moment, down the cost to develop the models, and because the impact of the state of the art of artificial intelligence and optimization affect directly the cost of these tools in this moment. It's very easy to sell this in a different way. I give the Danilo, can you speak, please?
Okay, Jesus. Hi, everyone. Okay, I will share my screen. Let me 1 second. So, okay. Okay. Hi, everyone. Let me check 1 second here. Um, yeah, sure. Okay. Um, Hi, my name is Danilo Abril. Uh, I am an industrial engineer with a master's degree in operation research. I am truly passionate about developing mathematical models to support decision-making processes in several industries or fields. Today, I'm going to present a model that we developed for the Sociedad Portuaria de Cartagena. It's an scheduling model designed to program the port operations. Essentially, the model assigns each vessel to a berth and a specific section of that berth, and also allocates the cranes that will handle its operations, loading and unloading operations. Okay, so as a result of this work, there are two publications. The first one is this one is presenting right now. Is in ORMS today. Is an article that presenting the business case and its benefits. Its benefits. What happened? Okay. The second one is academic article. Is published by Journal Logistics, and it contains the detail of a mathematical model in a solution methodology. Okay, so I would like to summarize how port operates. This will help set to the stage for the rest of the presentation, especially for the mathematical formulation that I will share. Okay, so here there are some geographic points in front of the port where the vessels must arrive to be served. When a ship reaches one of these points, we refer that moment as the arrival time. At that point, the vessels must wait for the tug box. And based on the operational schedule, the port dispatch the tug box, which also takes a local captain. This captain has a deep understanding of the port geography and the current conditions, allow him to safely guide the vessel from the arrival point to the assigned berth. This process is known as berthing time. After that, the vessel is docked in the part of the berth where it's allocated, and the operation starts in that moment. When I mean the task of unloading and loading and unloading tasks. once the vessel has been served, departure time here when the service serves a departure operation follows similar to the berthing procedure. This the departure phase essentially includes the time required to move the ship from the berth back to the arrival point, where the vessel's control is returned to the captain, and this moment marks the official departure from the port. Yeah. Why I give you this short introduction? Even though most people here probably know how a port works, this explanation is key to understanding a fundamental concept used in our optimization model, and this concept is the events. We adopted the definition of events used in discrete event simulation, and an event is any situation or milestone that change the state of the system. In our case, we work with two main events. The first one is the ship's arrival at the port, and the second one is the ship's departure from the port. Here, we are more closely at the berthing time, but I think that it's not necessary to spend time here. Let me check. Okay. So how now I will talk about how we build the model. Okay. So in this slide, we can see the different entities or indices that we consider when we building the model. I would like to briefly explain some of them. First, the Cartagena Port Society is composed by two terminals that these two they are at two separated geographical points with independent resources and coordinated operational autonomy. The Cartagena Port Society is a regional hub, which implies that the transfer of container between these terminals, since some containers may arrive at one terminal and leave the port through the other one. This represents a significant operational cost for the port, and it involves an additional operation if you compare it with other ports around the world. In fact, this is one of the main reasons why the model was commissioned or contract, and is a specific feature only seen in some ports around the world. Now, what is a service? A service is a route provided by a shipping line. A route is a set of ports visited in an order and periodic fashion, with commitments regarding the arrival date and the time at each port is visited. Another feature of a service is the ship, so the vessel that operated it is not always the same ship, because the same vessel, because a service may take 2 months to return to its starting port, but they operate in a weekly frequency. This is important because within the model, because it defines the physical characteristics of the vessel being serviced, and this must match the physical characteristics of the berth. For example, the berth must have the structural capacity and draft required to serve a specific vessel. There are different types of services, but I will mainly refer to the containers vessels. But there are also ships that transport vehicles, bulk cargo, etc., and this model applies to them also. Here we can see the set of variables considered in the model. I won't into detail about the indices. I will try to link them to some key variables to explain certain interesting constraints. First, we have the variable TIV. This is variable is a continuous variable that indicate the chip's arrival type at the port, and is associated binary variable AEE indicates that the event when chips enter to the port. Okay, and the variable TSS indicates the chip's departure time, and the associated binary variable AES represent that event. A very important point here is that the time is handled as a continuous variable. This allows for high precision and detail in the schedule activities. This is a major feature compared to other to formulation like timetables, where time is discretized and therefore some precision is lost in the results. This depends on the time slot used in the formulation, 2 hours, 1 hour, 15 minutes, or 5 minutes. A smaller time slots require more binary and integer variables, which can affect the solution times. We use two types of variables in the model: continuous variables for time management and binary variables to define the type of event occurring along the timeline. It's worth recall that our formulation is an event-based formulation. The first constraint ensures that the two events can occur at the exactly same time, and they must be separated by epsilon. And this condition comes from the stochastic processes. The second constraint we are seeing here state that every event must be categorized at either entry or exit event for each vessel. Taking into account that our model is event-based, we must estimate beforehand how many events are needed to the mathematical model. Any person can assign a number arbitrarily, but like everything in life, probably there must logic behind how the number is determined. I want to spend time in this slide. Here, I would like to explain how we handled the Berlin. It's crucial to consider that the quay has specific characteristics like such a draft and structural capacity. This determines which vessels can service at which section of the quay. These characteristics may not be uniform along the entire quay line. We could model the line as continuous, but this would imply infinite docking points, expanding the search space and negatively affecting the solution times. So what we do? We divide the quay into segments that are homogeneous in terms of the draft and structural capacity. Initially, a vessel could be located in any of those segments, but the chief also has physical dimensions to consider. In reality, she can dock in many segments, but the port operation already identifies certain reference segments where specific chiefs are usually berthed. Also, due to the ship's length, there are some segments that are impossible to be assigned to a dock. Handling the quay in this way reduces the number of possible combinations and makes the solution search page much more efficient. Here, the first constraints say that every chip must have an entry event and the corresponding event, exit event, that is defined by the second one. The third equation determines that when a vessel is assigned to a quiet segment, it will occupy the segment from the entry to the exit event. Now, the first constraints ensure that the chip is attending only in one bar of the terminal. The second one and the third constraint activates the TEV variable, which is the entry time to the port, linked to the variable assigning variable, the ver to the chip. The same idea applies to the departure time variables. Here, this is the constraint I want to explain. Basically, it synchronizes the ship arrival time TIV variable, yeah, with the event that marks the actual arrival at the port. When the variable AEE takes the value of 1, the two sides of the expression become 0, ensuring that the variable TIV and TIV and TAV and TEV are equal. Of course, this needs to write in two different equations. This way, the timing of the event is linked to the specific type of the event is occurring in that event. The same coordination, the same concept can apply to the departure variable time, that which is TSV, and its associated departure event variable AE is X. Now we have calculated the arrival and departure time of the vessel. We can measure the deviation from the service window, where the vessel is supposed to be complied with. Why are the deviation important? Okay, if a service or a vessel is not attend in the right time window, the port maybe have to pay penalties due to the deviation in the service delivery time window, because probably the vessel has to throw the Panama Canal. So if the vessel lost the appointment, probably had to wait a couple of days in order to can go through all the channel. Okay. 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 Similar as we define an event as ship's vessel arrival, we can also define an event for the moment where a crane is assigned to a ship. Likewise, we can define the moment a crane finishes the service, and it's important to highlight that the event phase formulations allow us for a high level of detail modeling detail. The coordination of events works the same way as show you, which is that what I'm presenting here, because the key point is to see or to show you the flexibility or versatility of this idea for coordinating multiple activities. If you would like to understand the model in detail, feel free to contact me or Jesus. We can schedule a 2-hour meeting to explain the full model. Basically, it's a large model with about 100 equations that reflect the port operations. In addition to the papers already available online, we also have material in-depth with in-depth explanation of the approach we've presented right now. As I mentioned, this is a large-scale model composed of approximately 100 equations. These equations represent different functions that allow them to be grouped in several groups. The first group is the YARAN, inventory and terminals and services. This component is related to the assignment of the services to the terminals. Associated with this assignment are some constraints related to the yard capacity where the containers are stored. The second one is the assignment component. We call this group correspond to a set of equation responsible for assigning the ships to the berths, as well also these the cranes that also this component assign the cranes that will service each vessel. It's not about the number of cranes, but in this case, the model assign specific cranes that will carry out the operation on the vessel. The third component is a set of equations that define operation times. You can see here in times. The operation time depends on the movement and the movement encapsulate the crane operation handling the containers. These blocks could be considered independent problems within the overall model, but in reality they have some connections, some communication points between them, and they are constraints that basically are constraints that they communicate these blocks of equations. In most real cases, trying to solve the model integrally is inefficient or some cases infeasible. While it is possible to solve the model as a monolithic model, this typically require very high computational times. In our initial test with a small instance and we obtain solution in reasonable times. However, when scaling to real instances, the solution times increase significantly, reaching the 8 to 10 hours without guaranteed feasible solutions. Given that this tool or this model is intended for daily operation use, it was essential to achieve much shorter response times in that moment. So here is important to remember one of the main motivations for building this model, and one of the reasons was the high operational cost resulting from the transfer between terminals. These transfers could represent a weekly cost that could exceed the $100,000 per week. In fact, if you assign the run terminal a service, it probably costs this kind of money per cycle. So we are talking about that one run assignment could value at $3 million US per year. Therefore, in order to get to solve the problem, we choose to divide the model into stages. The first one stage is the assignment the services to the terminals, considering the transfer costs between them and the available jar capacity. The objective was obtain a feasible assignment that minimized operational costs and ensure that each terminal had the capacity to handle its operation. It was necessary to add some constraints in order to include this condition in the solution process, which were not considered when we view the model integrally. The second part, is the operational scheduling between each terminal. Here the pink blocks. They solving the problem of assignment specific resources. It means claims to the chips to the bars, calculating the times and the movement involved. This stage allows for building the detailed operational scheduling. This approach allow us to solve the problem as a combination of assignment and scheduling. Once the assignment is done, the scheduling between each terminal the scheduling within each terminal can be executed in the separate way or independently, as there is not a direct interaction between them and at this stage of the procedure. Furthermore, within each terminal, we apply a block or group-based resolution strategy. For example, if a terminal is assigned to 20 chips during a 2-week operating cycle, they are grouped according to the arrival times. So the first 5 chips are scheduled initially, minimizing their service time. In the next iteration, 10 chips are scheduled, but we fix the solution obtained for the first group, and so on until all chips and all vessels assigned to the terminal are covered. This strategy significantly improves the solution times. Once a solution for the terminal is obtained, it can be refined by using the integrated model again, feeding the initial solution to the solver to identify possible improvements or adjustments. And this is in this slide we can see the methodology. The grouped runs can be clearly seen here. In each run subset, the unshaded blocket is the group of chips that to be scheduled. The purple boxes indicate the chips groups whose scheduling is already known and is fixed for that specific run. In this way, we complete the process, follow this scheme. First, the general assignment, the general model assignment is solved. The operational scheduling by block is carried out within each terminal, and when we obtain the solution, the solution is refined again. This is a graphical view of the result created by the model. We can see the bars, the line time, and where the vessels are attended by the claims. 。 We had internally named this composition a progressing resolution approach as a sliding optimization. We could say that we are the originator of this methodology. While it is a practical and efficient solution, we also consider applying a large-scale optimization techniques in a future work to accelerate the response times and increase the level of the operational detail that must be considered. Currently, the model coordinates the interaction between the maritime side and the land side of the port. However, more detailed levels of the scheduling must also consider it. For example, if necessary to coordinate the specific movements of each crane assigned to achieve establishing the optimal order for unloading and loading containers, minimizing unnecessary movements and improve the operational efficiency. Inside the ship, the crane maybe have to move some containers to access the one to be removed, and everything affect the port performance. Therefore, there should be model that inform or suggest to the crane operator which moving should be made. Later, the container has been unloaded, it must be transported and appropriately located in the yard. At this stage, multiple constraints and operational policies come into play, such as the container final's destination or if a scheduled departure on another ship. This decision should be made with the goal of minimization of distances, reducing energy consumption, and mitigating the environmental impact. Today, it's extremely important to reduce the carbon footprint of each company operations. I would like to share some uses this model has in the operation of Port of Cartagena. They are using the model for daily scheduling of terminal operations. At the tactical level, the model is used to assign the services to the terminal. And at the commercial level, they use the model to verify the port capacity to accept new services offered by shipping lines. The port achieve a strong positive impact on over the operation sport. Probably, I remember that the economical impact was evaluated around $3 million per year, basically because the model reduced the transfer cost between the terminals. And if I invite, finally, I think that I invite you to read the two articles that have resulted from this work to gain a better understanding of what has been presented today. And this is all for you, and thank you. If you have any question, is the moment. So if there is no question, thank you for your time, for hearing me, and goodbye.